The next speaker is Aldrich Louis. Aldrich is a trained chemical engineer, again from the University of Stellenbosch. Seems like everybody here is from Stellenbosch University. But he also has an advanced degree in management from the University of Pretoria, as well as he's got an MBA from the University of Cape Town. He's been employed at ArcelorMittal from 2008, and he was then appointed in 2020 to be the general manager of ArcelorMittal Saldanha site. And the focus of this was for new business ventures. And he apparently also enjoys the outdoor life and sports. So please, we are looking forward to hear about the new hydrogen ideas on green steel that you want to produce.
Honourable Mayor, members of the local council, as well as municipal management, leaders of industry, ladies and gentlemen, it's my privilege to be able to present at this very prestigious event. And personally, I'm a big admirer of the work that's being done by the Trust. But we're quite excited to present and to provide, let's say, the broader community an introduction or an update to this very exciting project. And from 2020, since the mothballing of the Saldanha Works facility, we've been looking at repurposing the actual site and also looking at other applications for the surrounding land as well. And so you can imagine we've been hard at work since 2021 on this very exciting project. And when we looked at the facility itself, we saw that the actual plant lent itself to this new upcoming and very exciting industry, and that's in the production of decarbonized green iron as well as green steel. And this is the project that we want to introduce today. It's a project very much still in its infancy. We're only looking to conclude pre-feasibility at the end of this year, and after that another couple of years before we reach a financial investment decision. But it's a project that we are hopeful that will be able to muster the necessary technical and financial solution and would be found to be feasible. Next slide, please. So maybe a little bit of background. Steel represents 7% of global emissions, and it's an important industry to decarbonize. And what I want to do is just to look at the various construction materials and how they compare to steel in its carbon footprint, as well as the ability to recycle those materials as well. And it shows I would say, the flexibility of steel and the fact that steel is an important material for the next phase of production, and that's in a decarbonized sense as well. So looking firstly at excuse me, can we go back to the previous slide? So firstly, if you look at steel, its carbon footprint compares well to materials like aluminium. The green shows you the initial carbon footprint during production. For steel, it's about 2 tons of carbon dioxide per ton of steel. Aluminium, of course, is much higher. Plastics are higher as well. And cement, or the production of cement as a construction material, has got a lower carbon footprint, but steel is much more recyclable. Between 85 and 90% of all steel is being recycled, and aluminium and plastic does not compare as favorably to that. And in producing steel from recycled resources, you find that the carbon footprint is much lower. So steel is very important as well in the production of the decarbonized solutions that are required. It plays a key role in wind turbines, in solar PV construction, as well as other construction materials that are very important in the decarbonization of our societies. Next slide, please. I think it's very important before we continue that we look at a couple of very important terminology or definitions. And the first one is that iron ore is the raw ore that we mine, and during the first step of refining, you form a material that's called either liquid iron or direct reduced iron or sponge iron. So liquid iron would be the material that's gone through its first step of refinement. direct reduced iron, and that's a liquid process. Direct reduced iron is a product where the oxygen has been stripped from the ore, and it's a very important input to electric arc furnace processes. And pig iron is also a refined iron product, although it's not steel yet. It still contains a large quantity of impurities, and also it contains a large percentage, or above 2.5 to 3% of carbon, so we still call it iron. Once it's gone through further refinement, we call it liquid steel, and these are the final products that we refer to as steel. And steel scrap as well is an important input to the production of steel as well. So in looking at it, iron ore is the virgin commodity that you require to produce high quality steels, and these are the various steps of refinement. Next slide, please. So maybe to take you through the actual the classic means of producing steel, and that's through the blast furnace process. And looking at Saldanha while it was in operation, its part of iron making was actually called the Corex process. It's the tallest when one looks at the various structures. And what you can see that most steel today is produced from primary resources. That would be iron ore. And in that process, you can replace about 20% of the input with scrap, although it's very energy intensive, so you require between 18 and 22 gigajoules of energy per ton of final steel produced. And you can look at that as about 400 kilograms of natural gas, and also very similar to that, your typical handy gas that you use at home. So very, very energy intensive. An important byproduct from the Corex or iron making process was granulated slag, and that becomes a very important input replacement in the cement process as well. Now, in looking at the process, very classic sense, coal and iron ore is used. You have a large amount of carbon dioxide emissions due to the fact that you're using coal. As well as, so for every ton of steel, you produce about 2.3 tons of CO2 emissions. Next slide, please. There are other means of making steel, one being the production of steel from scrap. So you've got scrap, you've got an electric arc furnace, and your carbon footprint is only about 0.4 tons of CO2 per ton of steel. The second means of doing that is where you have direct reduced iron. You use natural gas in the reduction of that iron ore. And then finally, you end up with a product using iron ore and direct reduced iron after it's been refined. And then finally, you have a carbon footprint which is lower than that of the classic process, which is from iron ore and coal, but still it has a high carbon intensity. Next slide, please. So maybe I think it's very important to look at some of the technicalities of the Midrex process, because it becomes clear as to why the Saldanha opportunity is so exciting, and that's specifically due to its installed infrastructure. Now, if one looks globally at what's happening in terms of the transformation of the steel industry to be decarbonized, it's in the construction of these direct reduction plants, and one of them is the Midrex plant. And as you would note that Saldanha Works already has a Midrex plant, so it already has the necessary infrastructure to produce a decarbonized steel. And this gives you an overview of the process, but essentially hydrogen and carbon monoxide in the Midrex process is already two important inputs in the reduction of this ore. And the hydrogen is formed by the splitting or reforming of natural gas. So natural gas is one carbon, 4 hydrogen. It's split into carbon monoxide and hydrogen, and that is reduced for reduction, produces a direct reduced iron, and it becomes a very important input in the electric arc furnace process. And why this is so interesting is that the use of hydrogen for reduction is not a new process. It's only the percentage hydrogen within the process that is being increased, and the source of the hydrogen now changes from natural gas to the direct electrolysis of water. Next slide, please. And just to give you an overview of the Saldanha Works technology, it had an installed Corex, it has the Midrix. It used to use coal and coke, so the combustion of coal in the Corex process produced carbon monoxide gas, small amounts of hydrogen. This was used for the reduction in the Midrix process, so you had two products. You had a liquid iron and a direct reduced iron. And Saldanha already has electric arc furnace technology installed. And what we had noticed was that there was all of the elements of a new green production facility. The only thing that needed to change now was, instead of using the gasification from the Corex process, to look at the water electrolysis in order to feed that direct reduction plant. Next slide, please. I think, so just a quick overview of how you decarbonize a Midrix process. You use green electricity, electrolyze that green electricity. That's physically taking the water, splitting it into hydrogen and oxygen, and this becomes your feedstock to your typical Midrix process. Or you can take the carbon dioxide formed when using natural gas, and you can store that underground in depleted natural gas wells or in salt caverns and other solutions. The third solution is to take the carbon dioxide, to convert it either through a biochemical process or a different chemical process, and to form ethanol and other products which could be captured in the form of plastics as well. But the route that we're aiming to take is the use of hydrogen, using the Midrix plant, and producing a product which we believe demand will grow dramatically in the market as we see further and further electrification of processes. Next slide, please. So I think we don't have to linger on the slide, but this spells out the technical solution. All of these processes are then, all of these chemical reactions are then removed. It's essentially the reaction of the iron ore with hydrogen to form elemental iron, and the byproduct then being water. And there's the ability to then recycle that water in the process as well. So the byproduct, instead of it being carbon dioxide in the past, from the Saldanha facility, it will now be a much cleaner, decarbonized emission, which is water, and a product we can recycle. Next slide, please. Maybe while we are switching to the next slide, there we go. So I think that ends the background, and now to summarize what the project is. We are looking to produce 1.2 million tons of direct reduced iron using hydrogen. That's for local consumption or export to places like the EU or the Far East. We have partnered with other industries or other big commercial partners in order to produce the hydrogen. Sasol is one. And recently we've brought in a competent renewable energy player in the form of mainstream renewable power as well. Our objective, our ambition is, excuse me, it's very ambitious. Excuse me. It's very ambitious, but we're looking to start up this facility by Q4 2027, Q1 2028. And it's still dependent or highly dependent on the ability to prove that it's commercially feasible, because we're going to require a commercially and a sustainable business model in order to attract the necessary funding to operationalize the process. Key findings that we've already found is that technically the plant is in good condition. It lends itself to this process, which is quite exciting for us. It does require some modification in order to accept hydrogen, but we believe it's definitely technically possible. There's quite a few strengths to the Saldanha location. It's where we sit. It's the fact that there's an existing deep water port versus other project. We've already got the technology installed, which reduces the risk as well. It de-risks the project, and it opens up the opportunity for investment. And then finally, we've got attractive renewable energy resources in South Africa. The project need, we project that by 2030, the demand for DRI will be around 190 million tons. Currently, only around 60 million tons of projects have been announced. So there's definitely a growing demand, and that demand is not being satisfied by the existing projects or planned supply. Next slide, please. So just a quick overview of the technical solution. How do you make green or hydrogen DRI? You need water, and you need about 610,000 cubes of water per annum. It's less than the water we used in the past during the operations of the site, and we'll dig into that a little bit more. So you need to desalinate water. That water gets fed into your electrolysis process. You need renewable energy. It can come from wind, solar, or other renewable resources. You split the water into hydrogen and oxygen. That oxygen can be used in the medical industry and other applications. You've got hydrogen, and that hydrogen moves to the actual Midrex process. You need about 61,000 tons of hydrogen per annum to fully utilize the facility. That hydrogen can also be used to produce other products. And then finally, the product, which is 1.2 million tons of DRI, can then be exported or used locally in the production of green steel. And this is what we are aiming to do. We expect that the international market for DRI will be much more willing to pay the necessary price or price premium for the product, and there will be a shortage internationally, so immediately international markets is our first aim, but there's good opportunities locally to produce green steel. Next slide, please. So just from a ramp-up perspective, it's our ambition to start producing the first DRI Q4 2027, 2028, and then start up the facility and then gradually ramp up until we reach full production by 2032, or if possible, we could do it earlier, depending on the uptake of the market as well and the development of the market. As you can see, this is the modifications that are required to the plant. And in comparison, so let's say the shaded sections are what's required. The blue and the red is what's already there. So as you can see, it's modifications to the plant, but most of the backbone of what is required to produce the green direct reduced iron or the sponge iron already exists. Next slide, please. I think water in the context of this session and in the context of our solution becomes very, very important. So typically in the past, in operation, Saldanha consumed around 6,000 cubes or cubic meters of water per day, up to 8,000 during at certain times. And it was a big part of that came from potable water and treated sewage water. And as a project, we now have to look at what is the right solution for the project that would be sustainable and would ensure that our impact on the surrounding environment would be minimized. So there's a couple of sources. The one would be potable water. We live in a water scarce area, so it needs to be carefully considered. Treated sewage water, we understand the impact of certain discharges into the bay. There may be a positive impact from using treated sewage water. The other one would be boil water. Of course, needs to be carefully considered in terms of its sustainability, if at all possible. And then lastly would be seawater desalination, and looking at what these seawater desalination could mean for this area if there's an abundance of water available for development, for agriculture, and for other applications as well. And this gives you a sense of how much demon water we would require per day. It's about close to 1,700 cubes of water per day. Next slide, please. I think just to look at the positive aspects of what we have in the Saldanha area and what we have in the facility that already exists. I think the one is that South Africa has got considerable iron ore endowment, and we need to look at ways of beneficiating that. And the Saldanha Works project creates that opportunity. The second one is then partnerships. It's partnership with other industry partners. It's partnerships with government. It's partnerships with entities like the trust as well as the community, in trying to see how do we jointly work together to make the project happen. I think we can acknowledge that partnership will be key to to this project actually seeing the light of day. Renewable energy resources, I think as South Africa, we've got an amazing mix of wind and solar strength, and we need to look at how we utilize that to produce the lowest cost hydrogen. We've got the existing Midex facility, which really adds to the feasibility of the solution. The next one is we are at a deep water port, meaning that the port is there. It enables the export of the product, as well as being on existing transport routes as well, which reduces our logistics cost. I think land will be key, land for the electrolyzers, and when necessary, land for renewable resources locally, if it does make sense. If it does not make sense, bringing in the renewable resources through the grid. Next slide, please. Thank you very much for the opportunity.